Hello and welcome. Today I will be reading from Calculus by Michael Spivak. This is an introductory textbook on analysis. The book is about calculus, and hence the name. However, it teaches analysis. The first chapter is called Basic Properties of Numbers. The title of this chapter expresses in a few words the mathematical knowledge required to read this book. In fact, this short chapter is simply an explanation of what is meant by the basic properties of numbers, all of which, addition and multiplication, subtraction and division, solutions of equations and inequalities, factoring and other algebraic manipulations are already familiar to us. Nevertheless, this chapter is not a review, despite the familiarity of the subject. The survey we are about to undertake will probably seem quite novel. It does not aim to present an extended review of all material, but to condense this knowledge into a few simple and obvious properties of numbers. Some may even seem too obvious to mention, but a surprising number of diverse and important facts turn out to be consequences of the ones we shall emphasize. Of the 12 properties which we shall study in this chapter, the first 9 are concerned with the fundamental operations of addition and multiplication. For the moment, we consider only addition. This operation is performed on a pair of numbers. The sum a plus b exists for any two given numbers a and b, which may possibly be the same number, of course. It might seem reasonable to regard addition as an operation which can be formed on several numbers at once, and consider the sum a subscript 1 plus a subscript 2 plus until a subscript n of n numbers a1 through to an as a basic concept. It is more convenient, however, to consider addition of pairs of numbers only, and to define other sums in terms of sums of this type. For the sum of 3 numbers, a, b, and c, this may be done in 2 different ways. One can first add b and c, obtaining b plus c, and then add a to this number, containing a plus b plus c. Or one can first add a and b, and then add the sum a plus b to c, obtaining brackets a plus b close brackets plus c. Of course, the two compound sums obtained are equal, and this fact is the very first property we shall list. Property 1. If a, b, and c are any numbers, then a plus the sum of b and c equals the sum of a and b plus c. The statement of this property clearly renders a separate concept of the sum of 3 numbers superfluous. We simply agree that a plus b plus c denotes the number a plus b and c equals a and b plus c. Addition of 4 numbers requires similar, though slightly more involved considerations. The symbol A plus B plus C plus D is defined to mean 1. A and B plus C all plus D. Or 2. A plus B and C all plus D. Or 3. A plus all of B and C plus D. Or 4. A plus all of B plus C and D. Or 5. A plus B plus C and D. This definition is unambiguous since these numbers are all equal. Fortunately, this fact need not be listed separately, since it follows from the property B1 already listed. For example, we know from B1 that A and B plus C equals A plus B and C, and it follows immediately that statements 1 and 2 are equal. The equality of statements 2 and 3 is a direct consequence of P1, although this may not be apparent at first sight. One must let B and C play the role of P in P1 and D the role of C. The equalities of the statements 3 equals 4 equals 5 are also simple to prove. It is probably obvious that an appeal to P1 will also suffice to prove the equality of the 14 possible ways of summing 5 numbers. But it may not be so clear how we can reasonably arrange a proof that is so without actually listing these 14 sums. Such a procedure is feasible, but would soon cease to be if we considered collections of 6, 7 or more numbers. It would be totally inadequate to prove the equality of all possible sums of an arbitrary finite collection of numbers A subscript 1 through to A subscript n. This fact may be taken for granted, but for those who would like to worry about the proof, and it is worth worrying about once, a reasonable approach is outlined in problem 24. Henceforth, we shall usually make a tacit appeal to the results of this problem and write sums A1 plus A2 plus through to AN with a blithe disregard for the arrangement of parentheses. The number 0 has one property so important that we list it next. Property 2. If A is any number, then A plus 0 equals 0 plus A equals A. An important role is also played by 0 in the third property of our list. Property 3. For every number A, there is a number negative A, such that A plus negative A equals negative A plus A equals 0. Property 2 ought to represent a distinguishing characteristic of the number 0, and it is comforting to note that we are already in a position to prove this. Indeed, if a number x satisfies A plus x equals A for any one number A, then x equals 0. And consequently, this equation holds for all numbers A. The proof of this assertion involves nothing more and subtracting a from both sides of the equation. In other words, adding negative a to both sides. As the following detailed proof shows, all three properties, P1 to P3, must be used to justify this operation. If a plus x equals 0, then negative a plus x equals negative a plus a equals 0. Hence, negative a plus x equals 0. Hence, 0 plus x equals 0. Hence, x equals 0. As we have just hinted, it is convenient to regard subtraction as an operation derived from addition. We consider a minus b to be an abbreviation for a plus negative b. It is then possible to find the solution of certain simple equations by a series of steps, each justified by P1, P2, or P3, similar to the ones just presented for the equation a plus x equals a. For example, if x plus 3 equals 5, then x plus 3 plus negative 3 equals 5 plus negative 3. Hence, x plus 3 plus negative 3 equals 5 minus 3 equals 2. Hence, 0 plus x equals 2. Hence, x equals 2. Naturally, such elaborate solutions are of interest only until you become convinced that they can always be supplied. In practice, it is usually just a waste of time to solve an equation by indicating so explicitly the reliance on properties P1, P2, and P3, or of any of the other properties we shall list. Only one other property of addition remains to be listed. When considering the sums of three numbers, a, b, and c, only two sums were mentioned. A and b plus c, and a plus b and c. Actually, several other arrangements are obtained if the order of a, b, and c is changed. That these sums are all equal depends on property 4. If a and b are any numbers, then a plus b equals b plus a. The statement of P4 is meant to emphasize that although the operation of addition of numbers, of pairs of numbers, might conceivably depend on the order of the two numbers, it in fact does not. It is helpful to remember that not all operations are so well behaved. For example, subtraction does not have this property. Usually, a minus b does not equal b minus a. In passing, we might just ask when a minus b does equal b minus a, and it isn't easy to discover how powerless we are if we rely only on properties P1 to P4 to justify our manipulations. Algebra of the most elementary variety shows that a minus b equals b minus a only when a equals b. Nevertheless, it is impossible to derive this fact from properties P1 to P4. It is instructive to examine the elementary algebra carefully and determine which steps cannot be justified by P1 to P4. We will indeed be able to justify all steps in detail when a few more properties are listed. Oddly enough, however, the crucial property involves multiplication. The basic properties of multiplication are fortunately so similar to those for addition that little comment will be needed, for both the meaning and the consequences should be clear. As in elementary algebra, the product of A and B will be denoted by A dot B or simply AB. Property 5. If A, B, and C are any numbers, then A dot BC equals AB dot C. Property 6. If A is any number, then A dot 1 equals 1 dot A equals A. Moreover, 1 does not equal 0. The assertion that 1 does not equal 0 may seem a strange fact to list, but we have to list it because there is no way it could possibly be proved on the basis of other properties listed. These properties would all hold if there were only one number, namely 0. Property 7. For every number A that does not equal 0, there is a number A to the power of negative 1 such that A times A to the power of negative 1 equals A to the power of negative 1 times A equals 1. Property 8. If A and B are any numbers, then A dot B equals B dot A. One detail which deserves emphasis is the appearance of the condition A does not equal 0 in B7. This condition is quite necessary since 0 dot B equals 0 for all numbers B, and there is no number 0 to the power of negative 1 satisfying 0 times 0 to the power of negative 1 equals 1. This restriction is an important consequence for division. Just as subtraction was defined in terms of addition, so division is defined in terms of multiplication. The symbol A divided by B means A times B to the power of negative 1. Since 0 to the power of negative 1 is meaningless, A divided by 0 is also meaningless. Division by 0 is always undefined. Property 7 has two important consequences. If A, B equals A, C, it does not necessarily follow that B equals C. For if A equals 0, then both A dot B and A dot C are 0, no matter what B and C are. However, if A does not equal 0, then B must equal C. This can be deducted from P7 as follows. If A dot B equals A dot C and A does not equal 0, then A to the power of negative 1 dot AB equals A to the power of negative 1 dot AC. Hence, A to the power of negative 1 dot A dot B equals A to the power of negative 1 dot A dot C. Hence, 1 dot B equals 1 dot C. Hence, B equals C. It is also a consequence of P7 that if A dot B equals 0, then neither A or B equal 0. In fact, if A dot B equals 0 and A is not 0, then A to the power of negative 1 dot AB equals 0. Hence, A to the power of negative 1A dot B equals 0. Hence, 1 dot B equals 0. Hence, B equals 0. It may happen that A equals 0 and B equals 0 are both true. This possibility is not excluded when we say either A equals 0 or B equals 0. In mathematics, or is always used in the sense of one or the other, or both. This latter consequence of P7 is constantly used in the solution of equations. Suppose, for example, that a number x is shown to satisfy x minus 1 times x minus 2 equals 0. Then it follows that either x minus 1 equals 0 or x minus 2 equals 0. Hence, x equals 1 or x equals 2. On the basis of the 8 properties listed so far, it is still possible to prove very little. Listing the next property, which combines the operations of addition and multiplication, will alter the situation drastically. Property 9. If A, B, and C are any numbers, then A times, in brackets, B plus C equals A dot B plus A dot C. Notice that the equation in brackets B plus C dot A equals B dot A plus C dot A is also true by property 8. As an example of the usefulness of P9, we will now determine just when A minus B equals B minus A. If A minus B equals B minus A, then, in brackets, A minus B, close brackets, B plus B equals, in brackets, B minus A, close brackets, plus B equals B plus, in brackets, B minus A. Hence, A equals B plus B minus A. Hence, A plus A equals, in brackets, B plus B minus A, close brackets, plus A, equals B plus B. Consequently, A dot in brackets 1 plus 1 equals B dot in brackets 1 plus 1. And therefore A equals B. A second use of P9 is the justification of the assertion that A dot 0 equals 0, which we have already made and even used in a proof on page 6. Can you find where? This fact was not listed as one of the basic properties, even though no proof was offered when it was first mentioned. With P1 through to P8 alone, a proof was not possible, since the number 0 only appears in P2 and P3, which concern addition, while the assertion in question involves multiplication. With P9, the proof is simple, though perhaps not obvious. We have A dot 0 plus A dot 0 equals A dot in brackets 0 plus 0 equals A dot 0. As we already noted, this immediately implies, by adding negative A dot 0 to both sides, that A dot 0 equals 0. A series of further consequences of P9 may also help explain the somewhat mysterious rule that the product of two negative numbers is positive. To begin with, we will establish a more easily acceptable assertion that negative A dot B equals negative in brackets A dot B. To prove this, note that negative A dot B plus A dot B equals, all in brackets, negative A plus A dot B equals 0 dot B equals 0. It immediately follows that by adding negative in brackets A dot B to both sides, that negative A dot B equals negative, all in brackets, A dot B. Now, note that negative A dot negative B plus, all in brackets, negative A dot B equals negative A dot negative B plus negative A dot B, which equals negative A, all in brackets, negative B plus B equals negative A dot 0 equals 0. Consequently, adding A dot B to both sides, we obtain negative A dot negative B equals A dot B. The fact that the product of two negative numbers is positive is thus a consequence of P1 through P9. In other words, if we want P1 to P9 to be true, the rule for the product of two negative numbers is forced upon it. The various consequences of P9 examined so far, although interesting and important, do not purely indicate the significance of P9. After all, we could have listed each of these properties separately. Actually, P9 is the justification for almost all algebraic manipulations. For example, although we have shown how to solve the equation x minus 1 times x minus 2 equals 0, we can hardly expect to be presented with an equation in this form. We are more likely to be confronted with the equation x squared plus minus 3x plus 2 equals 0. The factorization x squared minus 3x plus 2 equals x minus 1 times x minus 2 is really a triple use of P9. X minus 1 dot x minus 2 equals x dot in brackets x minus 2 plus negative 1 dot in brackets x minus 2. This equals x dot x plus x dot negative 2 plus negative 1 dot x plus negative 1 dot negative 2 equals x squared plus x, all in brackets, negative 2 plus negative 1 plus 2 equals x squared minus 3x plus 2. The final illustration of the importance of P9 is the fact that this property is actually used every time one multiplies Arabic numerals. For example, the calculation 13 times 24, which equals 52 plus 26 tenths, which equals 312. This is a concise arrangement for the following equation. 13 times 24 equals 13 times, all in brackets, 2 times 10 plus 4 equals 13 times 2 times 10 plus 13 times 4 equals 26 times 10 plus 52. Note that moving 26 to the left in the above calculation is the same as writing 26 times 10. The multiplication 13 times 4 equals 52 uses P9 also. 13.4 equals 1.10 plus 3, all times by 4, equals 1 times 10 times 4 plus 3 times 4 equals 4 times 10 plus 12 equals 4 times 10 plus 1 times 10 plus 2 equals 4 plus 1, all in brackets, times by 10 plus 2 equals 5 times 10 plus 2 equals 52. The properties P1 through P9 have descriptive names, which are not essential to remember, but are often convenient for reference. We will take this opportunity to list properties P1 through P9 together and indicate the names by which they are commonly designated. Property 1. Associative law for addition. A plus, in brackets, B plus C equals, in brackets, A plus B plus C. Property 2. Existence of an additive identity. A plus 0 equals 0 plus A equals A. P3. Existence of additive inverse. A plus negative A equals negative A plus A equals 0. Property 4. Commutative law for addition. A plus B equals B plus A. Property 5. Associative law for multiplication. A times BC equals A times B, C. Property 6. The existence of a multiplicative identity. A times 1 equals 1 times A equals A, where 1 does not equal 0. Property 7. Existence of multiplicative inverses. A times A inverse equals A inverse times A equals 1, for all A not equal to 0. Property 8. Commutative law for multiplication. A times B equals B times A. Property 9. Distributive law. A times, in brackets, B plus C equals A times B plus A times C. The 3 basic properties of numbers which were made to be listed are concerned with inequalities. Although inequalities occur rarely in elementary mathematics, they play a prominent role in calculus. The two notions of inequality, A is less than B and A is greater than B, are intimately related. A is less than B means the same as B is greater than A. Thus, 1 is less than 3 and 3 is greater than 1 are merely two ways of writing the same assertion. The numbers A satisfying A greater than 0 are called positive, while those numbers A satisfying A less than 0 are called negative. While positivity can thus be defined in terms of the greater than sign, it is possible to reverse the procedure. A is less than B can to be defined to mean that B minus A is positive. In fact, it is convenient to consider the collection of all positive numbers, denoted by P, as the basic concept and state all properties in terms of P. Property 10. Trichotomy law. For every number A, one and only one of the following holds. 1. A equals 0. 2. A is in the collection P. 3. Negative A is in the collection P. Property 11. Closure under addition. If A and B are in P, then A plus B is in P. Property 12. Closure under multiplication. If A and B are in P, then A times B is in P. should be complemented with the following definitions. A is greater than B if A minus B is in P. A is less than B if B is greater than A. A is greater than or equal to B if A is greater than B or A equals B. A is less than or equal to B if A is less than B or A equals B. Here we have a footnote, and that reads, there is one slightly perplexing feature of the symbols greater than and equals and less than or equals. The statements 1 plus 1 is less than or equal to 3, and 1 plus 1 is less than or equal to 2 are both true, even though we know that less than or equal to could be replaced by less than in the first and by equal in the second. This sort of thing is bound to occur when the less than or equals to sign is used with specific numbers. The usefulness of the symbol is revealed by a statement like Theorem 1. Here, a quality holds for some values of A and B, while inequality holds for others. Now we return to the main text. Note, in particular, that A is greater than 0 if and only if A is in P. All the familiar facts about inequalities, however elementary they may seem, are consequences of P10 to P12. For example, if A and B are any two numbers, then precisely one of the following holds. 1. A minus B equals 0. 2. A minus B is in the collection B. 3. Negative in brackets A minus B equals B minus A is in the collection B. Using the definitions just made, it follows that precisely one of the following holds. 1. A equals B. 2. A is greater than B. And 3. B is greater than A. A slightly more interesting fact results from the following manipulations. If A is less than B, so that B minus A is in P, then surely in brackets B plus C minus in brackets A plus C is in P. Thus, if A is less than B, then A plus C is less than B plus C. Similarly, suppose A is less than B and B is less than C. Then B minus A is in P, and C minus B is in P. So, C minus A equals in brackets C minus B plus in brackets B minus A is in P. This shows that if A is less than B and B is less than C, then A is less than C. The two inequalities, A less than B and B is less than C, are usually written in the abbreviated form. A is less than B is less than C, which has the third inequality, A is less than C, almost built in. The following assertion is somewhat less obvious. If A is less than 0 and B is less than 0, then A times B is greater than 0. The only difficulty presented by the proof is the unraveling of definitions. The symbol A is less than 0 means, by definition, 0 is greater than A, which means 0 minus A equals negative A is in P. Similarly, negative B is in P, and consequently, by P12, negative A times negative B equals A times B is in P. Thus, A times B is greater than 0. The fact that A times B is greater than 0 if A is greater than 0, B is greater than 0, and also if A is less than 0, B is less than 0, has one special consequence. A squared is greater than 0 if A does not equal 0. Thus, squares of non-zero numbers are always positive. And in particular, where we have proved a result which might have seemed sufficiently elementary to be included in our list of properties. 1 is greater than 0, since 1 is the square of 1. The fact that negative A is greater than 0 if A is less than 0 is the basis of a concept which will play an extremely important role in this book. For any number n, we define the absolute value of A as follows. The absolute value of A equals A when A is greater than or equal to 0, and negative A when A is less than or equal to 0. Note that the absolute value of A is always positive, except when A equals 0. For example, we have the absolute value of negative 3 equals 3. The absolute value of 7 is 7. And the absolute value of 1 plus root 2 minus root 3 equals 1 plus root 2 minus root 3. And the absolute value of 1 plus root 2 minus root 10 equals root 10 minus root 2 minus 1. In general, the most straightforward approach to any problem solving involving absolute values requires treating several cases separately, since absolute values are defined by cases to begin with. This approach may be used to prove the following very important fact about absolute values. Theorem 1. For all numbers A and B, we have the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. Proof. We will consider 4 cases. Case 1. A is greater than or equal to 0 and B is greater than or equal to 0. 2. A is greater than 0 and B is less than 0. 3. A is less than 0 and B is greater than 0. And 4. A is less than 0 and B is less than 0. In case 1, we also have a plus b is greater than 0, and the theorem is obvious. In fact, the absolute value of a plus b equals a plus b equals the absolute value of a plus the absolute value of b. So in this case, the equality holds. In case 4, we have a plus b is less than 0, and again, the equality holds. The absolute value of a plus b equals negative, or in brackets a plus b, equals negative a plus negative b equals the absolute value of a plus the absolute value of b. In case 2, when a is greater than 0 and b is less than 0, we must prove that the absolute value of a plus b is less than or equal to a minus b. This may therefore be divided into 2 subcases. If a plus b is greater than 0, then we must prove that a plus b less than or equal to a minus b, i.e. b is less than or equal to negative b, which is certainly true, since b is less than 0, and hence negative b greater than 0. On the other hand, if a plus b is less than 0, we must prove that negative a minus b is less than or equal to a minus b, i.e. negative a is less than a, which is certainly true again, since a is greater than or equal to 0, and hence negative a less than or equal to 0. Finally, note that case 3 may be disposed of with no additional work by applying case 2 with a and b interchanged. End of proof. Although this method of treating absolute values, separate consideration of various cases, is sometimes the only approach available, there are often simpler methods which may be used. In fact, it is possible to give a much shorter proof of theorem 1, and this proof is motivated by the observation that the absolute value of a equals the square root of a squared. Here and throughout the book, the square root of x denotes the positive square root of x. This symbol is defined only when x is greater than 0. We may now observe that the absolute value of a plus b all squared equals a plus b all squared equals a squared plus 2ab plus b squared, which is less than or equal to a squared plus 2 times the absolute value of a times the absolute value of b plus b squared, which equals the absolute value of a squared plus 2 times the absolute value of a times the absolute value of b plus the absolute value of b squared, which equals the absolute value of a plus the absolute value of b all squared. From this, we can conclude that the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b, because x squared is less than y squared implies that x is less than y, provided that x and y are both non-negative. A proof of this fact is left to the reader in problem 5. One final observation may be made about the theorem we have just proved. A close examination of either proof offered shows that the absolute value of a plus b equals the absolute value of a plus the absolute value of b if a and b have the same sign, i.e. they are both positive or both negative, or if one of the two is 0. While the absolute value of a plus b is less than the absolute value of a plus the absolute value of b if a and b are of opposite sides. We will conclude this chapter with a subtle point, neglected until now, whose inclusion is required in a conscientious survey of the properties of numbers. After stating property 9, we proved that a minus b equals b minus a implies that a equals b. The proof began by establishing that a times 1 plus 1 equals b times 1 plus 1, from which we concluded that a equals b. This result is obtained from the equation a times 1 plus 1 plus b times 1 plus 1 by dividing both sides by 1 plus 1. Division by 0 should be avoided scrupulously, and it must therefore be admitted that the validity of the argument depends on knowing that 1 plus 1 does not equal 0. Problem 25 is designed to convince you that this fact cannot possibly be proved from properties P1 to P9 alone. Once P10, P11 and P12 are available, however, the proof is very simple. We have already seen that 1 is greater than 0. It follows that 1 plus 1 is greater than 0. And in particular, that 1 plus 1 does not equal 0. This last demonstration perhaps only strengthened your feeling that it is absurd to bother proving such obvious facts. But an honest assessment of our present situation will help justify serious consideration of such details. In this chapter, we have assumed that the numbers are familiar objects, and that P1 to P12 are merely explicit statements of obvious, well-known properties of numbers. It would be difficult, however, to justify this assumption. Although one learns how to work with numbers in school, just what numbers are remains rather vague. A great deal of this book is devoted to elucidating the concept of numbers, and by the end of the book, we will have become quite acquainted with them. But it will be necessary to work with numbers throughout the book. It is therefore reasonable to admit frankly that we do not yet thoroughly understand numbers. We may still say that, in whatever way numbers are finally defined, that they should certainly have properties 1 through 12. Most of this chapter has been an attempt to present convincing evidence that P1 through P12 are indeed basic properties, which we should assume in order to deduce other familiar properties of numbers. Some of the problems which indicate the derivation of other facts about numbers from P1 to P12 are offered as further evidence. It is still a crucial question whether P1 to P12 actually account for all properties of numbers. As a matter of fact, we shall soon see that they do not. In the next chapter, the deficiencies of properties P1 through Pre-12 will become quite clear. But the proper means for correcting these deficiencies is not so easily discovered. The crucial additional basic property of numbers which we are seeking is profound and subtle, quite unlike P1 through P12. The discovery of this crucial property will require all the work of Part 2 of this book. In the remainder of Part 1, we will begin to see why some additional property is required. In order to investigate this, we will have to consider a little more carefully what we mean by numbers.